and use all of those matter in what you're actually getting. And of course, you can see void. So this is again low layer height. And what happens with higher layer heights is here I really don't see much of an interface defect. Again, this is optical microscopy. Scanning electron microscopy will show you. You've seen in the previous slide, depending on the layer height, you will see difference in voids. But what is important to note are these interfilament joints that you start to see, which are basically when the layers start to arrange themselves next to each other. This joint, this void that comes in. And if any of you have done multi-layered 3D printed structures and try to do any conventional durability test like an RCPT or a migration test, you will know this immediately. You will have an overflow of current very, very quickly in that direction. So that defect is there, depending on what your layering geometry is. So the question is, generally one filament with testing, which is done in many places, normally don't capture this effect. You have to do multi-filament testing. So one of the approaches that we did is to curve and stagger the filaments. So this is your conventional filament, the straight filament. You can shape it in a different form. So we have two different shapes. This I call an S shape, and this called a 3 shape. And we did some finite element modeling to understand and I'll show you what curvatures you need to ideally do this without your material flowing in all different directions. But if you do that, and then of course, cut beams and specimens from those printed slabs in that manner, now what you do is you don't align the interface or interfilament layers along the same direction. You induce crack tortuosity along the filament directions. Now, these two are slightly different in terms of how they are printed, and I'll show you that in a minute. So that's your layer width, that's your layer height. We have a radius of curvature of the filament, of the arc, and the radius of curvature, we kept the constant at 120 millimeters, and the chord length was also kept the constant at 100 mm. So just to make sure that the analysis captures similar effects. But you see here, this is smooth printing. You're not doing rapid turning of directions, whereas here you have an inflection in your printing direction. So that causes a little bit different effects as you look at specimens. So to quickly look at, we just did one mix. And again, the idea is not to look at what happens with different mixes. The idea is just to look at what happens with the printing effect. So just one mix, plain limestone, 30%. I mean, all of our mixes are now with at least 40 to 50% of cement replacement with limestone and fly ash and other things. So there's a 30% limestone mix. We've shown significant buildability, good compressive strengths, all of that in that. And then one with steel fiber and one with basalt fiber. Steel fibers, 13 millimeter long, 0.2 mm diameter. Basalt fibers, much smaller and much thinner. They do different things in the mix. And again, I'm not going into the fiber reinforced concrete discussion, but the idea is to look at different failure mechanisms. And the slabs were printed and specimens were cut out of those slabs for testing. And again, everything was printed using a gantry printer. So if you look at flexural strengths, again, this is, I think, very early age flexural strengths. We just want to make sure that we get the behavior correctly. So weaker interfilament joints in the linear printed conventional systems. For the S-shaped and 3-shaped, interfilament joints are creating more contact area between the filaments along this for the same length of the beam, and the curved paths ensure that the stress required to separate the adjacent filaments is higher, since the filament contact path, like I said, is more tortuous. So by simple change in geometry, you can actually see an increase in strength. Fiber reinforcement, just quickly looking at steel fibers, no surprises. You get much higher strength with steel fibers. Basalt fibers also give you higher flexural strength. Whereas if you do a staggered configuration, there is some increase, but not that much of increase. Basalt fibers, because they are much smaller, for the same volume fraction of fibers, you have about 13 times the number of basalt fibers in the mix. So they are spaced much more closely. They influence crack propagation much more effectively in that sense, but steel fibers provide a lot of ductility to the mix, which I'll just show you now. Both midpoint deflections are increased for both the cases. If you look at this picture, this is for the conventional linear and the staggered systems and the S-shape systems, whereas here you will look at linear and staggered S-shaped systems. So you see a higher midpoint deflection. You see with steel fibers, you see a strain softening, a higher toughness as well. Again, not completely for the steel fibers because of the layer orientation, but you can see the orientation effects without the fibers in this picture. So actually, you can change the orientation and do increase the properties significantly. Again, showing you a strains at the peak load. There is redistribution of strains as it cracks because now the crack paths are different. The strain concentrations are different because the way in which the filaments are oriented. Again, it's not the interlayer effects. The interlayers are the same because the layer thickness is the same. It is the interfilament effects, and therefore you will have differences in the way cracks propagate. Peaks, the maximum strains at peak stress are not really indicators. So this is not the exact strains that you will get if you put an LVDT and measure, because if you do an LVDT and measure it, you get local strains. These are generally the average strains across a specimen. There is a little bit of directional behavior in compression. I'm not showing directional behavior in flexure for a very specific reason. When you do flexural test and when you have your layers perpendicular to the direction of applied loading, then the layers influence flexure. The moment I flip it and make interfilament joints parallel to the direction, then I'm not doing a flexural test. The failure is along shear in that direction. You're not capturing flexure at all. You cannot use your conventional flexural equations to use that. So again, you see that mistake being made in a lot of publications where people flip it and do it and report a certain strength. Really, you're not testing flexure because there is not compression and tension alone, there is shear as well. So for that specific reason, we're not measuring, and we don't recommend measuring directional flexure. We do recommend measuring directional compression, because with compression, life is much more simpler. So if you have filaments arranged, if you're printing in this direction, so that's a layer and that's a filament, and the layers are built up, and you can see the direction 1 is along here, direction 2 is along here, and direction 3 is along here. You can see that there is definitely a directional effect on uniaxial compression. Direction 2, this direction, because it has much more of both interfilament and interlayer joints, direction 2 consistently shows higher strength. Some people call it XYZ. That's fair enough. I have difficulty doing X, Y, and Z because it's a cube. X, Y, and Z could be anything. Right? So I just say direction 1, 2, and 3 to make sure that we are not confusing different things. Okay. So layer orientation effects are less conspicuous in compression. The reason I said is that when you have overburden pressure, you're actually squeezing the layers, whereas anisotropy effects are dominant because of the interfilament effects. So if you print consistently, the interfilament effects are what is causing you your anisotropy. The interlayer effects generally are smeared unless you're using zero offset distance. In that case, you don't have consolidation, you will see layer effects. And especially when you're using smaller layers, you have less conspicuous layer effects. Anisotropy is evident, lower strength when textured in direction 2. Again, the idea that if I have just a linear print, not any other shape, I have about 70 to 100 square millimeter of interfilament, this vertical joint area, compared to 9,000 for staggered print cube. So when I have more interface area, basically I'm staggering all of that. The crack will have to do more work to go through the entire specimen. You will see slightly higher strengths. Effect not dominant in directions 2 and 3 for compression. So just to conclude, very simple change in print geometry. Again, I just showed you S and 3 shape geometry. We have several other geometries that we have done, which are much more complex. The idea is, yes, complex geometries will give you much better toughness, will give you much better behavior, but then complex geometries will create that much more complication actually printing in the field and actually layering it in the right orientations and directions. So we want to keep it simple. You have higher flexural strength compared to the regular prints. Again, staggering by half a layer width. Again, I forgot to tell you that all the layers were staggered by half a layer width, so that it's like you do masonry with bricks staggered, right? Very similar idea. Changes in print layout minimizes stress concentrations, while staggering induces tortuosity in the layer path. And we have microscopy to actually show how, which I did not show here, to show how the crack path changes. A more brittle behavior indicated in conventional prints, you can get, I won't say that it increases ductility, but it increases your peak strengths and peak strain slightly. The overall area increase under the curve is not large enough to call it an increase in ductility, because we typically use ductility associated with fiber reinforcement. But that you definitely see that effect. And a combination of fibers and orientation effects is definitely useful. So thank you very much, and I can take any questions.
I think you said it pretty clear. Okay, let's thank our, we have one. Okay.
I have a question. So did you see any difference in crack pattern when you're loading differently, both for compressive strength and any specific crack pattern when you're loading perpendicularly for flexural strength?
Yeah, so I'll talk about the compression first. There is difference in crack pattern when you load in compression different directions, because in one direction, the direction 2, you have much more of interfilament joints in it, which means a crack just goes through the interfilament joints. It's just a separation. Now, you can't even say that it is a new crack that's forming. It just nucleates and it just goes through the interfilament joints. If you do flexure, if you have a beam and you're loading it perpendicular to the direction of the layers. If you look at it, the layers are this way and the filament is this way, right? So multiple layers and the filaments this way. And if you load like this, now if you're doing a 4-point loading or a 3-point loading, if you are avoiding that interfilament joint, then you are actually loading this beam like something with a notch right in between, right? So this is, you can look at it as a system with a crack that is running through and through. There is a connection. It is not completely disconnected, but you think of a weak joint. So you have bonded 2 different materials, like a repair case. You've bonded 2 different materials. It's not a perfect bond, and you're loading in between. And that's why I said it becomes a shear case, not a flexure case, right? So yeah, you see that difference if you do that.
Thank you.